Welcome back, and time to get at these derivatives of inverse trig functions. So for this stuff, we have to assume we're within the appropriate domain, and under those conditions, then we can differentiate for sure, okay? We will do sine and tangent and then summarize. So the idea with the inverse trig functions, and the whole reason we need to pause and do implicit differentiation, is because we're actually going to employ techniques from implicit differentiation. So what I'm going to do is now the idea with an inverse trig function is that the input and output would switch. So I'm going to do that. I'm going to switch the inputs and outputs. I'm going to do x is equal to sine of y, right? And then next I'm going to say, okay, well, I want to differentiate this, but I'm going to differentiate with respect to x. Okay, well, what do I get when I do that? So I differentiate the left side, I get 1, and then now the right side is where implicit differentiation comes into play. Derivative of sine is cosine, right? Cosine of y, and then chain rule says I have to also multiply by dy dx. Okay, well, that's fine. And isolate dy dx by moving cosine over. Okay, so 1 over cosine of y is equal to dy dx. Okay, I'm done, right? Well, not really, because I need to express this in terms of x, right? So how do I do that? Well, okay, I remember that, let's see, 1 over cosine, okay, and then I remember the Pythagorean identity, right, is, okay, so this is a quick aside, so, cosine squared of theta plus sine squared of theta is equal to 1, and if I were to isolate cosine, that would be the same as 1 over square root of 1 minus sine squared y, yeah, okay, is equal to dy dx. All right, that's fine. But then sine y, oh wait, sine y was the same as x. So this is really just 1 over square root of 1 minus x squared. And that's the same as dy dx. Oh, that's kind of neat. Okay. So truthfully, there was another way you could have got that. You could have made a triangle perhaps or something, but this way would work as well. Okay, so again, switch the inputs and outputs, differentiate, and then try and use some known identities to help you rewrite the derivative. Similar, okay, so cosine is similar. We're not going to worry about that. We'll get to the derivative of inverse cosine in a moment, but for tangent, right? So let's begin the same way. So I'm going to do y is equal to tangent of x. Switch inputs and outputs. X is equal to tangent of y. Differentiate this with respect to x, d dx. Okay, so then I get 1 is equal to secant squared of y dy dx. Okay, so then dy dx. Okay, so then 1 over, we're just mirroring the steps that we did with sine, okay, secant squared. And I know secant squared, there's another Pythagorean identity that says 1 plus tangent squared of theta is equal to secant squared of theta, right? So I'm going to use that in my work and say this is really 1 over 1 plus tangent squared of y is equal to dy dx. Oh, and tangent y was the same as x. Oh, look at that. Isn't that pretty? 1 plus x squared in the denominator is equal to dy dx. And that's the derivative of arctangent. Okay, and so the summary there, we have the sine, arcsine and arctangents derivatives that we already saw. And then our cosine. Now, these domains here, keep in mind these would be the ranges of the original functions, right? So that's why we see this. And similarly, we could limit the ranges to be between, negative pi over 2, pi over 2, 0 and pi, and then all real, or negative pi over 2 exclusive, right? So just bear in mind that these are the ranges that are shown for the original function. The domain for the original functions are still restricted. Okay, so get these in your notes wherever you have all the other derivatives going, and then we're going to use these in some examples coming up.